let's take a look at the chemistry Regents reference tables, table by table, and make sure that you know all the bits and pieces of information here that might be helpful for the Regents exam. All right, so let's start with Table A. Table A, as far as standard temperature and pressure, usually the number one place you're going to use this is with any kind of gas law problem with the combined gas law, where either you're starting with conditions of STP, which stands for standard temperature and pressure, or the gas is going to be set at STP for the second scenario. So standard temperature and pressure for standard pressure, typically 101.3 kilopascals or 1 atm, and this is also the conversion of one to the other if you needed to know that. And for standard temperature, 273 Kelvin, of course, is 0 degrees Celsius. However, remember with the combined gas law, your temperatures always have to be in Kelvin. All right, for reference table B, we have the physical constants for water. These tie in directly with the heat equations and also the heating curve slash cooling curve. Heat of fusion, fusion, don't be confused, means melting. It takes 334 joules of energy per gram of water to either freeze it or to melt it. And heat of vaporization, of course, that is taking water and boiling it or condensing it. Specific heat capacity for water you see is 4.18. It's joules over grams times Kelvin. Now the reason for the Kelvin here is because there is a delta T that we're involved with when we're dealing with a substance, in this case water as a liquid, at one phase. So there is change of temperature when it comes to either warming or cooling, a gas only, a liquid only, or a solid only. Remember, heat of fusion and heat of vaporization are with phase changes, and at phase changes, your temperature is being held constant. Let's go down to reference table C. Reference table C, it says selected prefixes, but we know that means as far as the metric system. Now, if you have to go between one unit and another, there are these factors here that you can use, conversion factors, to get you from one unit to another. A lot of students, including some of my own still, will slide the decimal using King Henry's Drunken Uncle drinks chocolate milk. Now, there aren't too many questions that usually show up as far as a conversion factor for the metric system. But if you needed to take a look, of course, you would look at reference table C. Reference table B gives us selected units as far as the name, the symbol, and the quantity they represent. You probably know all of these fairly well from taking chemistry the entire year. I don't think students look at this table that much either, just like reference table C. Atomic mass unit down here, of course, has to do with the mass of a proton or a neutron being 1 AMU, which represents about 10 to the 20 minus 24 kilograms in mass, but we use atomic mass units in chemistry. And of course, the time ones would come into play maybe with half-lives, right? If you forgot what the symbols represent for things like days, minutes, years. But I just don't think you're going to be looking at D too much, but it is here if you need it. Reference table E. Now, this is one of those tables that you don't want to forget about because you're talking polyatomic ions. So this is a biggie. It gives you, of course, the name of the poly, including the charge. And remember, when you have a compound that contains a metal and then more than one nonmetal, you have a polyatomic ion for sure. And there's a couple here that I just want to point out, right? When we're dealing with acid-base chemistry, bases we use well, we don't use, but hydroxide ions when we have more hydroxide ions than hydrogen, also known as hydronium ions, then we have a basic solution. Hydronium ions are used interchangeably with hydrogen ions or H plus. That's an acid-base chemistry. But you might want to refer to this table if you're asked to name a compound or write a formula, or for that matter, you need to break things up into ions. For instance, for our next table, which is reference table F. Reference table F, it says it's solubility guidelines. By solubility guidelines, what we mean is what's soluble in water and what is not soluble, better known as insoluble in water. As it says down here, compounds having a very, very low solubility. In order to use this table, you would take a compound formula. For example, let's take Na2SO4. And you would break apart this ionic compound into its ions. So that's why I was saying reference table E also comes into play. So when I break it up into its ions, I have sodium ions and sulfate ions. And now I want to figure out whether this compound is soluble or insoluble in water. Well, just start from left to right. My sodium ions all of a sudden right away show up there. Group 1 ions, including sodium ions, are soluble in water. This is soluble in water. I don't have to look any further. If I was looking to see for sulfate, because I didn't find anything as of yet, then I would come down here. All sulfate compounds are soluble except for these exceptions, but sodium's not one of them. So literally what you want to do is break apart the compound into ions and then find one or both of the ions on reference table F. And it's either going to be in the solubility category or in the insoluble category. Reference table G. Now, table G isn't that much different than what we saw with reference table F, except now we have numbers that we can associate with how soluble a solute is in a solvent. But we're talking specific solvents here, like potassium iodide or sodium nitrate or potassium nitrate. So it's not the generalness of the last reference table. This is more specific. Not only is it specific as far as the solute, it's specific in terms of the temperature here on the x-axis and in terms of the amount of water that this or any of these solutes will dissolve in, which is 100 grams of water. So for instance, if you're asked, let's say you're at 40 degrees and you have 50 grams of potassium nitrate in 100 grams of water at 40 degrees, you're right here. Let's find 40, go up to 50, and we're right here. And we're comparing it as far as potassium nitrate. We're below the solubility or the saturated line for potassium nitrate. We would say that this solution can hold more solute. I can dissolve more. It is an unsaturated solution. In order for potassium nitrate to be saturated in 100 grams of water at 40 degrees, I'd have to come up to about 63, 64 grams of potassium nitrate in 100 grams of water at that temperature. So it's specific. You want to look it up on table G. The other thing I want to point out is most of these solutes, as the temperature increases, you can add more, an increase in solubility. However, there are a few solutes here that decrease in solubility. One of them is here, HCl, another one SO2, and another one NH3 known as ammonia. They're decreasing with an increase in temperature because they are gases. Gases are less soluble in water at higher temperatures, but solids are more soluble in water at higher temperatures. Let's keep moving on. Reference table H. This is vapor pressures and temperature. Notice that This is only for 4 different substances. Every liquid is going to have a vapor pressure curve, meaning you're going to have a change in vapor pressure depending on temperature. And notice the trend is the increased temperature, you increase the vapor pressure. This is um, with a liquid, how easy that liquid can go into the gas phase. So propanol has the weakest attraction between the molecules because it vaporizes a lot easier. And then all the way on the other side, ethanoic acid, of course, has the strongest intermolecular forces because the vapor pressure is lowest at any of the temperatures in this range. Normal vapor pressure is, of course, at um, standard pressure, which is 101.3 kilopascals or 1 atm. So if you're asked about the normal boiling point for any of these 4, it's where their curve crosses the dotted line. So if you're asked anything about vapor pressure, take a look at reference table H. One other question that's come up in the past, don't get tricked. If you're asked about which of the following is at the highest vapor pressure, and let's say it's the same liquid, but you have different containers, different closed containers at different temperatures, and you're asked which one will have the highest vapor pressure. It's going to go by the highest temperature, right? Vapor pressure, temperature. There's nothing here about volume. So it doesn't matter if you have a small container or a very big container. Your vapor pressure is dependent on your temperature. Reference table I. For reference table I, you're dealing with heats of reaction, in other words, your delta H's. So you have a whole bunch here of combustion reactions, which you'll see are all negative values, meaning they're exothermic. Then we have the formation of some compounds here, which are endo or exothermic. And then we have salts going into solution. Some are endo, some are exo. And then finally, we have the neutralization of hydrogen with hydroxide ions and forming water. Now it tells you here the little footnote that when you have a negative delta H, you have an exothermic reaction. And if you were asked to put the energy back into the reaction, remember you're going to put it in on the right-hand side, the product side, as a positive value. When you have a positive number here on reference table I, you have an endothermic reaction, and that number goes in on the left-hand side or as a reactant. So the other thing to keep in mind is that these values have to do with the moles, right? The coefficients in front of all the different substances. So for example, the more I form aluminum oxide, the more moles of aluminum and oxygen I have, the more energy that would be released. Remember that delta H also ties in with potential energy diagrams. So if I have a potential energy diagram, let's say it was of that formation of aluminum oxide, it's exothermic, so that's why aluminum oxide is lower in energy than the aluminum and oxygen to start. And then as far as delta H goes, remember that that's here. I'm just trying to draw some dots, right? So in between is my delta H. Okay, so if you're asked anything specific about delta H, or you think you have to memorize something, you don't. You have to look at reference table I. Let's switch over to reference table J. For reference table J, we are dealing with what's known as the activity series that is related to the redox unit. So we have a table for metals and a table for nonmetals. Okay, of my metals, lithium is the most active, meaning lithium wants to lose electrons the most. So lithium atoms will become lithium ions and an electron, right? That's oxidation. That means all the way here at the bottom, gold wants to lose electrons the least, and typically it's the gold ions that will grab an electron and become gold atoms. or however many. I have to check the oxidation number, but that's how it works. So when you have two metals, let's say it's for a voltaic cell, it's a manganese half cell and a magnesium half cell, and you want to know, well, what's going to be oxidized and what's being reduced. Magnesium is higher, so that's the half cell that's going to undergo oxidation, and the manganese then will be reduction. The other thing to keep in mind is that hydrogen here, almost all the way to the bottom, your copper, your silver, and your gold will not react in an acid. The metals above will, and the higher the metal, the more violent the reaction. On the nonmetal side, it's the opposite. Fluorine wants to gain electrons the most. So it wants to be the most active as far as reducing or gaining electrons. And that makes everything below it want to lose the electrons, okay, or be oxidized. So remember, when you have a redox reaction and you have the gaining of electrons, okay, a fluorine atom has 7. If it gains one more, it's going to have 8, and it'll be the fluoride ion. But in this case, since you have 2 fluorines, because it's diatomic, 2 electrons, so I have 2 fluoride ions. So again, fluorine wants to get reduced the most. 3 of the most helpful, I was almost going to, 3 of the most helpful, let's try this again, reference tables are the next 3, K, L, and M. K, you got all your common acids, so you got names and formulas, you got your common bases, and you have your indicators. Let's start with the indicators. Of course, your pH scale, below 7 is acidic, 7 is neutral, above 7 is basic, and just match the pH and the color range to figure out what's going on with an indicator. As far as acids go, acids, of course, are going to be either donating H plus, or you get H plus in solution. And first of all, the names are easy because they all have the name acid in them. And typically they start with H first. The only one that's a little weird is ethanoic acid, but remember that's an organic acid. For your bases, that's your metal and OHs. The exception is ammonia. Ammonia is a base when you look at it as far as a proton acceptor with the Bronsted-Lowry theory. So when you're trying to identify or name an acid or a base or figure out what's going on with indicators, don't forget about these 3 tables. With nuclear chem, you're going to use reference table N and reference table O. Now, reference table N gives you all information. It gives you nuclides. Nuclides mean that they are radioisotopes, meaning they are radioactive. How are they radioactive? They're spitting out particles and or energy. And as far as the particles, that's where the decay mode comes in. The rate at which it's decaying is known as the half-life. So you don't have to guess on these, you just have to know where to look. Now, as far as balancing nuclear reactions or providing the missing particle, that's where you're going to go to reference table O. Table O gives me names, notations, and symbols for all the different particles. Okay, your alpha particles are protons and neutrons. Overall, it has a +2 charge. Your beta minus is negative. Gamma radiation is no mass, no charge. It's just radiation. Of course, as far as neutrons go, you know, of course, they have no charge, but they do have mass. Protons have a mass of 1 and a charge of 1, and a positron has virtually no mass or little mass, just like an electron, except it's positively charged. So don't forget about reference table O. There's some good information here when it comes to nuclear chem and even atomic structure that you might want to refer to. All right, we're almost there. Let's take a look at organic. All right, so with organic chemistry, we have reference tables P, Q, and R. P are all those prefixes. It tells you the number of carbon atoms in a chain. Then you get to hydrocarbons. That's hydrogen and carbon atoms only. We have alkanes, alkenes, and alkynes. Remember, your alkanes, all single bonds, they are saturated hydrocarbons. Alkenes and alkynes have multiple carbon-carbon bonds. In the case of alkenes, it's a double bond, and alkynes, it's a triple. They are known as unsaturated hydrocarbons. Use the general formula also. If you're given the name of a hydrocarbon and you're asked how many hydrogens, then reference table R. Reference table R has all of the additional elements that would go on an organic compound. So organic means you have carbon atoms in the compound, then usually you have lots of hydrogens, and then anything else you're going to see here. Now, just like with any of the units, I went through other videos uh, with what to expect on the Regents exam. Go over any of that you're not sure of. You still have time to brush up on any of those units. But if we take a look quick here, we have the halogens in our halide group, one oxygen here in the next four, the alcohol, ether, aldehyde, ketone groups, two oxygens here in our organic acids or our esters, and then finally nitrogen in both amines and amides, but the difference between them, an amide also has oxygen. So when you're doing organic, just like when you're doing nuclear or acid base for sure, you should have these reference tables open. Okay, how could I forget about the best reference table at all, which of course right now is is you'd have to turn your head 90 degrees to see it. Probably throughout the whole exam, you should go right away and have the periodic table open. You know there's tons of information here. You got your electron configurations, you got atomic numbers to figure out protons, neutrons, and electrons. You have oxidation numbers for redox and figuring out charges on ions. Trends, you can use that in association with the next table. Let's go to reference table S. Reference table S. There's so much information here that you don't want to forget about. So numbers, symbols, names, there's no excuse when it comes to names. It's all here. First ionization energy, electronegativities, melting, boiling, densities, atomic radius, which you would use for size of the atom. So first ionization energy and electronegativity, make sure you know the definitions. I have a great video on that with the 7 terms you must know. So listen to it after you're done with this. If you really don't remember what those terms are, you can use this to look up individual physical properties for any element, or again, for trends, you would pick out either going across the table or down a group and then figure out trends. Another thing that's subtle sometimes are the density values. You know, it might ask you a question. There was a question about copper and figuring out percent error. And my students were having trouble because they're like, oh, I'm missing a piece of information. No, they forgot that the true value for the copper density was right here on reference table S. Okay, here we are at reference table T. So with reference table T, we have our formulas and our equations. The density formula, of course, E is M over V. Don't forget there's also densities on reference table S. Moles. If you're given mass and you need to find the number of moles, or you're given moles and you need to find the mass. Don't forget the gram formula mass. You're going to look up the masses on the periodic table. You're going to multiply by the number of times you see it in the formula, add those up, or sometimes in a question it's given to you. You just plug it in. Percent error, just follow along. Make sure you know from reading the question what's the measured value, meaning the student value, versus the accepted or true value. Percent composition, that could come up with percent by mass of an element in a compound. It also could come up with percentages in solution, parts per million. That's with concentration and also molarity. Now, don't get confused between the molarity equation and the mole equation. Yes, the word mole is in both, but you're given other pieces of information. So please reread the question to figure out which equation you need. Molarity, by the way, is a capital M. Combined gas law, it's the only gas law you need to know. You can cross anything out that's constant on both sides of the equal sign. Temperature has to be in Kelvin, and your pressure and volume units just need to be consistent on both sides. Titration equation is here. I would label or put the formula for the acid on the acid side and the base on the base side. And don't forget, this is used with the word neutralization as well. Yes, those heat equations. There's only one where you throw in the change of temperature, and that's when you're dealing with one phase only, and there is a change. Remember, phase changes happen at temperatures, but the temperature is not changing, so you don't see a delta T for the last two. Remember, the constants for water are on the front of the reference table, and then finally temperature. In Kelvin, we cannot go into the negative realm, but in Celsius we can. So remember, you can have a negative Celsius temperature. Well, that is the last reference table for the Regents Chemistry exam. I hope that you do well. I hope you keep working a little bit longer and harder tonight to get yourselves ready. Just walk in tomorrow, do the best that you can, and good luck.